In 1859, the sun screamed at the Earth. Not with sound, with a wall of magnetized plasma traveling over 1,000,000 miles per hour. It set telegraph offices on fire. It lit the sky from the Arctic to the Caribbean. And it happened before we had power grids, before satellites, before the internet, before everything that keeps you alive today was plugged into an electrical socket. It already happened. And when scientists went looking for evidence of how many times it has happened before, what they found in the rings of ancient trees was not reassuring. This is the story of the 3 times the sun attacked, the 1 time we got lucky, and the next shot that is already loaded. We built our entire civilization on one unspoken assumption: that the sun is stable. And for the most part, it is. It has been burning hydrogen for 4.5 billion years and has enough fuel for another 5 billion. But stability is not the same as calm. Beneath that golden surface, the sun is a churning ocean of superheated plasma, threaded with magnetic field lines that twist and tangle like rubber bands stretched to the breaking point. When those field lines snap, in a process called magnetic reconnection, they release energy equivalent to billions of hydrogen bombs. That energy does not just make light. It launches 1 billion tons of magnetized plasma into space. 1 billion tons. For reference, that is roughly the mass of every building in Manhattan combined, accelerated to speeds that would cross the distance from the Earth to the Moon in under a minute. Scientists call these eruptions coronal mass ejections. The sun fires off hundreds of them every year during active periods. Most sail harmlessly into the void between the planets. But when one of these clouds hits the Earth's magnetic field head-on, it does not knock on the door. It kicks it in. September 1st, 1859. A British astronomer named Richard Carrington was sitting in his private observatory in the small town of Redhill, just south of London, sketching sunspots. It was routine work. Then, at 11:15, 2 points on the sun's surface suddenly flared with brilliant white light. Carrington watched, stunned, for 5 minutes as the flare blazed and then faded. He had just witnessed one of the first solar flares ever observed by a human being. He did not know what he had set in motion. Roughly 18 hours later, the plasma wall hit. What followed was the most intense geomagnetic storm in recorded history. The sky erupted. Aurora borealis, normally confined to the Arctic, blazed across the entire planet. People in Cuba, Jamaica, Hawaii, and Colombia looked up and saw curtains of red and green light dancing overhead. In the Rocky Mountains, gold miners woke up and began making breakfast, convinced the aurora was the glow of sunrise. It was 2 a.m. A journalist at the San Francisco Herald wrote that the whole sky appeared to undulate like a field of grain in a high wind, and that the waters of the bay reflected the brilliant hues with a grandeur that was almost bewildering. It was beautiful. But beauty is the ultimate trap. The world's only electrical network at the time was the telegraph system, roughly 100,000 miles of wire strung across continents and under oceans. When the storm hit, those wires became antennas. The Earth's magnetic field was convulsing so violently that it generated electric currents in the ground itself, and those currents surged into the telegraph lines. Sparks erupted from the keys. Operators were shocked. At least one was knocked out of his chair. Paper tape caught fire in offices across America and Europe. Telegraph pylons burst into flame. And then something happened that bordered on the impossible. On the Boston to Portland line, operators disconnected their batteries entirely and continued sending messages powered by nothing but the storm. The aurora itself was generating enough current to run the system. The atmosphere had become the battery. We call this the Carrington Event. For over 160 years, it has been the benchmark for how bad space weather can get. But it was not the worst thing the sun has ever done. It was not even close. In 2012, a doctoral student at Nagoya University in Japan named Fusa Miyake was doing something remarkably simple. She was counting tree rings. Specifically, she was analyzing the carbon-14 content of annual growth rings in the stump of a 1900-year-old Japanese cedar. Carbon-14 is a radioactive isotope created in the upper atmosphere when cosmic radiation collides with nitrogen atoms. It drifts down, gets absorbed by plants, and is locked into tree rings year by year, creating a chemical diary of cosmic violence stretching back millennia. In one ring, grown in the year 774 to 775 AD, Miyake found something that made her stop. A 12% spike in carbon-14 concentration. That does not sound dramatic until you understand the scale. Normal fluctuations from the solar cycle produce changes of about 0.5%. The Carrington Event, the most powerful solar storm in modern history, produced a carbon-14 increase of less than 1%. This ring showed 12%, 20 times the normal variation. Whatever had happened in 774 AD was at least 10 times more powerful than the Carrington Event. A murder written in wood. She published her findings. Other teams raced to check. They tested wood from Germany, Russia, the United States, Finland, and New Zealand. Every sample showed the same spike, at the same year. Whatever happened, the entire planet experienced it simultaneously, and buried in historical records, there was a clue no one had connected before. The Anglo-Saxon Chronicle, written by monks in medieval England, recorded that in the year 774, a red crucifix was seen in the sky after sunset. The monks had no concept of solar physics. They wrote down what they saw and interpreted it as a sign from God. Modern scientists recognize the description for exactly what it was. An aurora. A blood-red aurora visible from England, the kind that only appears when the sun fires something monstrous at the Earth. Since Miyake's discovery, researchers have found 5 more of these events scattered through the tree ring record. 12,450 BC, 7,176 BC, 5,259 BC, 664 BC, and 993 AD. Scientists call them Miyake Events. They occur roughly every 2,000 to 2,500 years on average. But the intervals are irregular. The 2 most recent were only 220 years apart. There is no schedule, there is no warning. And a candidate event from 12,350 BC, identified in tree rings from the French Alps, may have been more than double the magnitude of any other known Miyake event. We do not know how bad it can get, because the sun has been relatively polite during the entire span of human civilization. Every city ever built, every empire that ever rose and fell, every war ever fought, and every technology ever invented has existed inside a window of solar mercy. We have been building our world during a quiet period. Quiet periods end. Now here is where the numbers become personal. In 2012, physicist Pete Riley published a paper in the journal Space Weather that asked a simple question. Based on 50 years of solar storm records, what is the probability that a Carrington-class event hits Earth in the next decade? His answer was 12%. 1 in 8. He said he was initially quite surprised that the odds were so high, but the statistics appeared to be correct. That means over a 50-year span, there is roughly a 50-50 chance of a direct hit from a storm that would have civilization-altering consequences. And that calculation is for the smaller one, the 1859 version, not a Miyake event, just a Carrington. But the probability was not the real shock. The real shock came 2 months later. On July 23, 2012, the Sun fired. A massive coronal mass ejection, the fastest ever recorded by NASA's Stereo spacecraft, tore through the exact orbital path that Earth follows around the Sun. It was traveling at over 6 million miles per hour. It was Carrington class. The magnetic field embedded in the cloud was pointed sharply southward, the worst possible orientation, meaning it would have coupled directly with Earth's own magnetic field and poured energy into the magnetosphere with maximum efficiency. According to Daniel Baker, professor of atmospheric and space physics at the University of Colorado, if the eruption had occurred only 1 week earlier, Earth would have been in the line of fire. Nine days. Nine days of orbital rotation separated modern civilization from an electromagnetic catastrophe. NASA's Stereo A spacecraft, sitting right in the path, recorded the full blast. Baker later said he came away from the studies more convinced than ever that Earth and its inhabitants were incredibly fortunate. Janet Luhman, a research physicist at UC Berkeley, put it more bluntly. Had it hit Earth, it probably would have been like the big one in 1859, but the effect today, with our modern technologies, would have been tremendous. A 2013 study estimated the damage at $2.6 trillion. We missed it. Most people never even heard about it. Then imagine this. It is 2 in the morning on a Tuesday in May of 2024. A farmer in central Iowa is asleep 18 time zones away. A sunspot group designated AR 3664, a magnetic region 17 times wider than the diameter of Earth, has been erupting for 3 days straight. It has launched at least 8 coronal mass ejections directly at us, including an X8.7 flare, the most powerful of solar cycle 25. The resulting geomagnetic storm has just reached G5, the highest level on NOAA's space weather scale, the first extreme-class storm in more than 20 years. The farmer does not know any of this. What he knows is that when he walks outside to check on the irrigation system, the sky is wrong. The horizon is glowing a deep, pulsing crimson. He is standing in Iowa, 1,000 miles south of where aurora should ever be visible, and the sky looks like it is bleak. The next morning, his GPS-guided planting system has drifted off course. Rows that should be perfectly straight are wandering. Across the Midwest, precision agriculture equipment is reporting errors. Satellites overhead are struggling. They named the storm after space weather physicist Jennifer Gannon. Aurora appeared on every continent. And on Mars, NASA's Curiosity rover recorded its highest ever radiation spike, a dose equivalent to 30 chest X-rays for a human standing unprotected on the surface. The Gannon Storm was a warning shot, not a Carrington, not a Miyake, a reminder. But here is what keeps engineers awake at night. We already know what a moderate storm does to a modern grid, because we watched it happen, live, in the dark. March 13, 1989. A coronal mass ejection hits Earth's magnetosphere and finds a weakness in the electrical system of Quebec. The province sits on a bed of ancient rock with very low electrical conductivity. That rock cannot absorb geomagnetically induced currents, so the currents have nowhere to go but up into the power grid. At 2:44 in the morning, they find their way into the Hydro-Quebec transmission system. 90 seconds. That is how long it took for the entire provincial power grid to collapse. 6 million people woke to darkness and sub-zero cold. A mother in Montreal opens her eyes, reaches for the light switch, and nothing happened. The heat is off, the stove is off, the radio is off. Outside, the streetlights are dead in every direction. She cannot call anyone because the phone network runs on electricity too. The blackout lasted 9 to 12 hours. The Montreal Metro shut down during the morning rush. Dorval Airport closed. Schools stayed dark. And 1,500 kilometers to the south, the same storm quietly destroyed a generator step-up transformer at the Salem nuclear power plant in New Jersey. That was a moderate storm, roughly a 1-in-50-year event. The modern grid was designed to handle something that size. The Carrington Event was at least 10 times stronger. A Miyake Event was 100 times stronger. The critical vulnerability is a machine most people have never thought about. The extra high voltage transformer. These form the backbone of every national power grid. They step voltage up for long-distance transmission and back down for local distribution. Each one costs around $10 million. Each one weighs hundreds of tons and requires specialized rail cars to transport. Each one takes 5 months to over a year to manufacture. Most of them are built overseas, in a handful of factories in Europe and Asia. There is no strategic stockpile. When geomagnetically induced currents flow through transmission lines during a storm, they enter these transformers and saturate their cores with direct current. The transformers overheat, the windings melt, and unlike a blown fuse, you cannot replace a destroyed extra high voltage transformer by driving to the hardware store. Current estimates for replacement lead times run 4 to 6 years. A severe storm does not need to destroy every transformer on a grid. It only needs to take out a handful at critical nodes, and the cascading failure spreads outward like cracks in glass. The difference between the 1989 storm and a Carrington event is not a few more hours of darkness. It is months of regional blackout, with no clear timeline for restoration. No refrigeration, no water pumping, no hospital power, no internet, no supply chain. The $2.6 trillion estimate assumes a Carrington-class event. No one has seriously modeled what a Miyake event would do to a connected, electrified, internet-dependent global civilization. The answer may be too uncomfortable to publish. So what can we do? We have exactly one defense. Time, not decades of time. Hours. When the sun fires a coronal mass ejection, we can see it leave. Space weather observatories like NOAA's Space Weather Prediction Center monitor the sun continuously. A typical CME takes 1 to 3 days to cross the 93 million miles between the sun and the Earth. Even a fast one, Carrington Fast, gives us roughly 15 to 18 hours of warning. In that window, grid operators can reduce loads, disconnect vulnerable transformers, and power down satellite lines can reroute flights away from the poles where radiation exposure spikes. Astronauts can shelter in the most shielded sections of the International Space Station. 15 hours is not a lot, but it is not nothing. The problem is that this defense depends entirely on detection, communication, and coordination, on governments and utilities choosing a controlled blackout over an uncontrolled one, on spending money to protect against something that has a 12% chance per decade of happening and that most voters have never heard of. The sun is not our enemy. It is our life. Every calorie of food you have ever eaten was built from sunlight captured by a plant. Every breath of oxygen in your lungs was released by photosynthesis powered by that star. We owe everything to the sun. But the sun does not know we exist. It is a ball of plasma governed by physics, and every few centuries, the physics produces a sneeze. The last major sneeze missed us by 9 days. The one before that knocked out a province. The one before that set telegraph offices on fire. And buried in tree rings around the world, there are scars from sneezes so violent they would have ended the modern world before it began. Somewhere on the surface of that star right now, magnetic field lines are twisting, tangling, storing energy in invisible knots that will eventually snap. The trees will record it. They always do. Patient and indifferent, writing the sun's diary in radioactive carbon, one ring at a time. The only question is what we will find when we look up one night and the sky is the wrong color, and the lights in every window on the street blink out one by one, and the silence that follows is not the sun's silence anymore. It is ours. If you found this fascinating, subscribe and stay curious. We have only scratched the surface of what the universe is hiding from us.